that we know what a sparse matrix is and how it is stored behind the scenes, let's look at how we would create one directly within MATLAB. So there's a variety of different calls depending on your application that you can use to make a sparse matrix. This first one is SparseAlloc. If you know that you have an m by n sparse matrix with nz non-zero entries, you can allocate the space in memory. This second function is also useful. Let's say that you have a dense matrix A, which is stored, and you want to convert it to sparse. You can just call sparse on A, and now you have a corresponding sparse matrix. So in the prior example with our tridiagonal dense matrix, we can convert it to being a sparse matrix by just calling the sparse of A, and use that for our later computations. Let's say that you know the row and columns array, so you already have the triplet format. You can input that as well as the size and number of non-zeros to sparse. There are also features to create matrices of a specific structure. So let's say that you know you're going to have a sparse matrix of all ones. You can call SP1s on S, where S is already a sparse matrix, and MATLAB will find its row and column arrays behind the scenes. You can also create the sparse identity using SPI of MM. You would always want to use this command rather than I. In general, if you can avoid forming the identity, that would be even better than using sparse I. We know that when we multiply anything by the identity, we get that matrix back itself. So if you can work through the linear algebra computations without explicitly forming the identity in memory, that would be advantageous. We can also create uniformly distributed random matrix. So if S is a sparse matrix, we can input that to SPRAND, where S has a specific sparsity structure. We can also specify that we want approximately mn times row non-zeros and a condition number of k by calling SPRAND with this syntax. We have the analogous function to create a sparse normally distributed random matrix. Similarly, if you want a sparse symmetric uniformly distributed random matrix, we can call SPRAND sim with the following notation. SPConvert allows you to import from sparse matrix external format. So lastly, one of the most useful is going to be to create sparse diagonal matrices. So we want to avoid using the diags command, as we did in the prior video, because we saw that the storage required is gigantic. So to create a sparse diagonal matrix, which is desirable, there are several commands that you can use. So let's say you want to create the sparse diags of A. This will return them in the vector B as well as D, identifying which diagonal you've extracted. Recall that 0 is the main diagonal, 1 is the super diagonal, increasing up until the highest diagonal. -1 is the first below subdiagonal, decreasing down. Okay. You can also extract the diagonals of A specified by D. So let's say we're only interested in the tridiagonal format, then D would be the vector -1, 0, 1. We can replace the diagonals of A specified by D with the columns of B. And lastly, you're going to use this in the next exercise. This is one of the most useful calls because we can provide B in a matrix format, as well as the indices of the diagonal D and the corresponding size, and make a sparse diagonal matrix stored in A. So let's see how we can use that command to properly form the tridiagonal matrix A. We're going to then compare the memory usage for sparse diagonals versus diags by looking at bytes. And let's see how much storage we save. So I'd like you to try this exercise now. Now let's go over the solution in sparse diags solution. So we'll see that the command is even less verbose than diags. We can say sparse diags, we're going to give this corresponding matrix where each diagonal is given by the column. So we see that our subdiagonal corresponding to -1 is given by this 1's vector. Then we have -2 on the main diagonal by 0, and we also have 1's on the first upper diagonal. And then we're saying the size is m by n. So if we run this code, we're going to see that the number of bytes now is only 39,980, which is much less than 8 million. So we're saving a huge amount of memory. In particular, this is 200 times less. Now, if we did have AD and wanted to convert it later, I'm just showing you here using the Boolean is equal function that calling sparse of AD returns the exact same as AS being used by sparse diagonal. So hopefully this example shows you the advantage of sparse storaging in tridiagonal cases.